Hello everyone, this is Jiri and this is Machine Learning in Economic Stream. Today we met because we have an interesting topic to discuss. It's the work is called Bounded Rationality in Las Vegas, and it concerns probabilistic fine automate play multi-armed bandits. My name is Jiri. I'm a stream owner at ACE. I'm also a data scientist. ACE is a community of machine learning practitioners and researchers who have gathered around three topics in AI, namely research, engineering, and product. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, visit our website, ai.science, and log in to access to slide of this presentation and other streams and presentations we have facilitated in the past. And also make sure that you subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and other free content we publish. We currently have 14 streams like this one and focus on various machine learning topics. And this is in machine learning in an economic stream. Hope you enjoy and come back. I would like to introduce you Xinming Lily Liu. She's an incoming PhD student at MIT Operation Research Center. She recently graduated from Cornell University, and in her future research, she will focus on operation research. So Lily, thank you for joining us, and I'm giving you my word.
Okay, cool. Thank you, Jerry, for the introduction. Hi, everyone. I'm Xinming, or you can call me Lily. I recently graduated from Cornell with double majors in computer science and operations research. In the fall semester, I will be starting my PhD in Operations Research Center at MIT. I'm very happy to present at ACES today and at a new spotlight series, Machine Learning in Behavioral Economics. The paper I'm going to talk about is called Bounded Rationality in Las Vegas, Probabilistic Finite Automata, PlayMulti-Armed Bandits. It recently got published in Uncertainty for AI conference, and it's joint work with Professor Joe Halpern from Cornell University. So traditionally, the economics always assume that people are fully rational and always maximize expected utility. So in other words, they will estimate the probability and payoff of each consequence and choose the ones that leads to the largest utility. In reality, however, we see many irrational behaviors. For example, people don't save enough for their retirement plans, or we often select the first or second items when we shop on Amazon. And Professor Don Ariely from Duke University actually conduct many experiments to show some systematic mistakes that people usually make in everyday life. And he wrote a book about it. It's called Predictably Irrational, and it's a really good book, and I highly recommend to take a look at it. So we begin the study by asking ourselves, is it possible that people are indeed rational, but simply have limited resources like memory or computational power? And we decided to look at a concrete example of gamblers playing slot machines. Imagine you're at a casino in Las Vegas. If there are 100 slot machines to choose from, and each of them has a different success probability, your goal now is to find the best one in order to maximize your long-term payoff. And this is, in fact, a multi-armed bandit problem. So what is the multi-armed bandit problem? Imagine you have K arms that you can pull. Each arm offers a set of possible rewards, and each obtained with some probability. You do not know the probability in advance, but you can learn them by playing the arms for sufficiently many times. And the MAB problem is a standard way of balancing the trade-off between exploration and exploitation. So to explore, we want to pull as many arms as possible. However, we also want to pull the arm with the highest success probability most often. So that's what we mean by exploitation. And formally, we can define a k-arm MAB as a tuple, mu1 to mu k. Each mu I is the distribution over the possible rewards of arm I. In this paper, we assume there are only two possible rewards, 1 and 0. So in that case, mu I just represents the probability of you getting a reward 1. We also assume that the distributions do not vary over time. We can easily modify the protocol to deal with a finite set of possible rewards, as long as we know them in advance. There are many protocols for the MAB problems, and one of them is Thompson sampling. It uses Bayesian methods, which means that we update the success probability of arms after each pull using the Bayes rule. And another one is the epsilon greedy. It explores with probability epsilon and otherwise exploits. Both protocols are pretty popular in the MAB literature, and but they use infinitely many states, and therefore are not very human-like. So in contrast to the previous work on MAB, we wanted to instead find a more human-like protocol and to explore the human behaviors. So our high-level goal is to model resource-bounded agents using a human-like protocol that uses relatively few states and are nearly optimal. We hope to show that given limited resources, human behavior is actually quite rational. Before diving into the protocols we propose in the paper, I wanted to quickly go over some background concepts about bounded rationality and cognitive heuristic. So Hubert Simon, back in 1955, actually brought up the idea of bounded rationality, which means that rationality is limited. When individuals make decisions, they may appear to be irrational due to the cognitive limitations of the mind and the time available to make the decision. So we follow closely with Simon's idea of bounded rationality and look particularly into memory resources. A heuristic is a mental shortcut that allows people to solve problems and make judgments quickly and efficiently. Again, introduced by Simon, the notion of satisficing is a decision-making strategy that searches through the available alternatives until an acceptable threshold is met. So basically, we're accepting things that are good enough instead of spending time to go through all the options to find the best one. Optimistic bias is another cognitive heuristic that causes people to believe they themselves are less likely to experience a negative event. And the last one I want to cover is the negativity bias. It is the notion that even when of equal intensity, things of a more negative nature have a greater effect on people's psychological states and processes than neutral or positive things. Therefore, people often react more quickly to negative outcomes. With this background concept in mind, let's now take a look at how we can capture resource boundedness. We decided to model resource-bounded agents as probabilistic finite automata. A PFA is just like a regular finite state machine with states and inputs, except its action and transition functions are probabilistic. So as you can see in the figure, the transitions are with some probability. And we also wanted our automaton to produce an output, basically tells us which arm to pull, rather than accepting a language. So technically, we are looking at what have been called probabilistic finite automata with output, or probabilistic transducers. So now the question becomes, can we find good PFAs for the MAB problem? We first come up with an idea of elimination tournament, which is to compare arms in pairs until we find the best one. Specifically, we alternate playing 2 arms for about n steps and keep track of the relative successes using a counter. We use a counter threshold M here to decide which arm is the winner and eliminate the loser. We repeat until only one arm is left and keep playing that arm from then on. Note that we stop a comparison with probability 1 over n. This ensures that we won't get stuck with 2 equally good, or in the worst case, 2 equally bad arms. We could have used another counter here, but that would cause us more states. The elimination tournament protocol uses finite states, approximately 2k² times m, where k is the number of arms and m is the counter threshold as mentioned before. But it's not really human-like because people may not alternate between 2 arms so systematically. It can be very costly to remember which arm to play. Also, it can be very costly to switch practically. Imagine 2 slot machines quite far from one another in a casino. I don't think a gambler will run back and forth to pull the arms. To tackle the problem, we therefore proposed the second expiration level protocol. And the big picture is to run a tournament to compare each real arm against the virtual arm and stop as soon as we find a good enough and hopefully the best arm. So what exactly is the virtual arm? It's just a success probability that you hope some real arm will beat. The probability is represented by ranks. For n possible ranks, rank R corresponds to a probability interval, R minus 1 over m to R over m. And we take the midpoint as the success probability. So the corresponding success probability is P equals to R minus 0.5 over m. And we start optimistically with rank m. So we want to start high and gradually lower the aspiration level as we as we go in the algorithm. So similarly to the previous protocol, we run a tournament for each real arm I against the virtual arm, and also use a counter to track the relative successes of arm I. However, since we're not playing against a real arm, it is a bit different how we update the counter. We do so probabilistically. So every time we pull arm I, if there is a success, we increase the counter by 1 with probability 1 minus p. That, as I mentioned before, p here is the success probability of the virtual arm. So 1 minus p is the probability that there wasn't also a success with the virtual arm. So basically there is a success with the real arm, but there wasn't a success with the virtual arm. So that's why we need to increase the counter by 1. And again, if there is a failure with the real arm I, we decrease the counter by 1 with probability p. So as an analog to the previous point, p here is the success probability of the virtual arm. Again, back here. That's why we decrease the counter by 1 with probability p, because that means there wasn't also a failure with the virtual arm. I, if counter hits m, it's a threshold similar to the protocol, but here we call it m stop. And we keep playing arm I from then on. If the counter hits minus m switch, we go on the arm 1. Notice here we have 2 different thresholds, m stop and m switch, which I will talk a bit more in the next slide. And if at the end, if no arm beats the virtual arm, that means we're too optimistic and our aspiration level is too high. So we need to lower the aspiration level. And we do so by decreasing the rank R by 1 and restart the tournament. So why do we need two different thresholds, M stop and M switch, instead of just one in the first protocol? So the intuition behind is that if a real arm wins the tournament, basically we are done and we keep playing that arm from then on. However, if the virtual arm wins, we just continue to look for another hopefully better arm because we just move on to the next arm. The cost of mistakenly saying that an arm to be optimal, a wrong arm to be optimal, is much higher than the cost of temporarily eliminating an arm that might be optimal, because we will always go back and look through all the arms. So therefore, we want M stop to be larger than M switch. Another question is, how can we quickly reach the appropriate aspiration level? A problem may come if, say, the best probability is low. For example, it's only 0.25. And the number of rank is large. Say we have 100 possible ranks. That means we have to start from 100 and gradually lower to about 25 or lower than 25. That's when we stop. So it will actually take a quite long time to reach the appropriate aspiration level. To tackle the problem, we come up with a solution by adding a pre-processing phase. So basically in the first phase, we can quickly figure out the approximate best success probability and then homing on that. So basically in the first pre-processing phase, we want to lower the ranks quickly, and in order to get an approximate idea of what the best success probability might be. And specifically in phase 1, the pre-processing phase, every time we need to lower the aspiration level, we decrease rank R by square root of M rather than 1. So say if we have 100 possible ranks, so when M equal to 100, square root of M is 10. And every time we decrease R by 10, when we need to lower the aspiration level. So again, we start off at 100, but instead of going to 98, 99, 98, we just directly jump from 100 to 90, 80, 70, and so on. Also, we will use smaller values of M stop and M switch. These changes will enable us to quickly find the aspiration level. And once we have a real arm that beats the virtual arm, we stop the pre-processing phase and let R star be the first rank at which a real arm wins the tournament. And this implies that the best arm it has success probability in the interval R star minus 1 over M to R star plus square root of M over M. And in phase 2, instead of starting from the very top, we actually used R star plus square root of M as our initial aspiration level. And we go back to decreasing the rank by 1 this time. So again, just give a numerical example. If the true best success probability is 0.25, and we take 100 possible rank, so M equals to 100, and then in phase 1, we again start with 100. Every time we decrease by 10 because the square root of M is 10. And our R star here will be 20 because again, it needs to go below the true success probability. That's when the real arm will beat the virtual arm. So our R star here is 20, and therefore we start our phase 2 with rank 30 instead of rank 100 because that's R star plus square root of M. So in this way, we can quickly find the approximate idea of the appropriate aspiration level, and we don't need to start from very top and then gradually lower it. So the aspiration level protocol, as I spent the previous few slides to go through, it is finite state. It is also quite human-like because firstly, we start with a high aspiration level optimistically. And secondly, we declared the optimal arm once a real arm wins the tournament. This corresponds to the notion of satisficing. Recall that it means to search through alternatives until a threshold is met. So we basically search through all the possible arms until a real arm beats the virtual arm. That means until a threshold is met. Thirdly, we use a smaller M switch. Sorry, we use a smaller M switch to temporarily eliminate arms, and that leads to the notion of negativity bias, which means that people react more quickly to negative outcomes. So once you lose the game, then you just quickly get moved on to the next arm. And finally, we want to evaluate the performance of various protocols. We first define the expected cumulative reward of protocol P for MABB and for about n steps. It is defined as the sum of the expectations of all the mu i's at time t from 1 to n. So each mu here is the reward of each arm played at step t. And we can define the expected regret as the difference between the maximum rewards and the expected cumulative reward for n steps. So here we have our mu b star as the maximum reward of an MAB problem. And that's why the n times mu b here means the maximum reward you can get if you keep pulling the best arm for about n steps. And again, the BPN, as defined before, is the expected cumulative reward if we are using protocol P. So basically, the expected regret, you can think of it as the difference between what we could have got in the best case scenario minus that what we will actually get using the protocol. And the limiting average regret is defined as the average of n-step regret as n goes to infinity. So it's an limiting behavior that we want to see what the average regret will be if we play it for infinite many of times. Well, the expected cumulative regret depends on how long it takes to find the best arm, because the longer it takes you to explore different arms, the more regret you might incur in the process. So that so the expected cumulative regret depends on how long it takes to find the best arm. The expected limiting average regret measures how good the chosen arm is. So say when you only have one arm left, and that one is indeed the optimal arm, then your expecting limited regret will be 0, because from then on you will keep playing the optimal arm for infinite many of times. However, if the protocol is not as good as the optimal one, it might end up with a good enough but not the best arm. So in that case, you might have, so we might incur a positive average limiting regret in that case. So so essentially, we want to find the best arm quickly and accurately, because we want the protocol to have both a low expected cumulative regret and also a low expected limiting average regret. We say a protocol is optimal if the limiting average regret is 0. Basically, as I mentioned before, if we end up with the optimal arm. And from then on, we just keep playing the optimal arm. We will have 0 limiting average regret. A stronger notion of optimality also takes cumulative regret into consideration. So that means it not only finds the optimal arm, but do so quickly.
Can I have a question, Lily?
Yeah, sure, go ahead.
Just a clarifying question. Can you go to the previous slide with expected cumulative regret? So is it expected cumulative regret a logarithmic function, or how would you describe it? I just didn't didn't get it.
Yeah. So again, if we look at how we define expected cumulative regret, it's just the difference between so n times mu b here is the maximum regret we can get. Just keep pulling the best arm for n steps, right? And the cumulative reward here is defined as the expectation of all the possible rewards of the rewards you get by pulling each arm at step t. And how we decide which arm to pull depends on the protocol. And so if we're looking at the previous aspiration level protocol, and so basically at each step, the protocol will tell you which arm to pull. And mu I of the arm I is the reward that we will get if we pull that arm. So basically, by definition, I would say it's a linear function in terms of the protocol, and the protocol will tell us which arm to pull. Hope that clarifies the.
Yes, that clarifies. I just I just didn't know how better to imagine it. But thanks.
Yeah, so it's just the difference between the best case scenarios and what we'll actually get if we're using the protocol.
Awesome, thank you.
Yeah, no problem. Okay, so just continue what we said before. We say the protocol is optimal if the limiting average regret is 0 for all possible MABs. A stronger notion will be it will also take into consideration of the cumulative regret. So again, Jerry, the clarification question you ask, I think, is very helpful to understand the definition of optimality, because this is the next thing I'm going to show. So you mentioned like how is the cumulative regret defined, and it's like a linear function of our protocol, but depends on different protocols that we are chosen. For example, for Thompson sampling is one of the one of the famous protocols for MAB problem. There's lots of proof saying that it will converge. It will converge to the optimal arm quickly in the stronger notion. That means that's how we define the cumulative regret, and it grows logarithmically. So that means basically the theorem here states that for Thompson sampling, it's not only optimal in the sense that it has 0 limiting average regret, but it's also in a stronger sense because it's cumulative regret divided by log n. Gets to a constant CB star, and that constant is optimal. That constant is the smallest possible one. So that's what we mean by Thompson sampling is optimal in a stronger sense. And however, as we prove a theorem in our paper, actually no PFA can be optimal. So basically it means that its limiting average regret is always positive. So it's always at least epsilon that's greater than 0. However, we can make our protocol as nearly possible by just choosing different parameters so that the epsilon is as small as possible. Okay, cool. So now I want to like show some simulation results to see how our protocols will compare with other different protocols. In the simulation, we'll look at an MAB with 50 arms, and we assume that the success probabilities are uniformly distributed in 0 and alpha. So here alpha is just a random number between 0 and 1. So say alpha can be 0.5. So basically we say the 50 arms are uniformly distributed between 0 and 0.5. So we could have assumed that they follow a uniform distribution in 0 and 1. Because if that's the case, it's very so if we instead assume a uniform distribution in 0 and 1, then the best success probability is almost surely close to 1, because we're assuming that there are 50 arms distributed between 0 and 1. Then it's very likely there's an arm in between the interval from, say, 0.9 to 1. If that's the case, then the problem that it takes too long to reach the appropriate aspiration level will never occur, and we don't need a two-phase protocol at all. And also, if we think about Las Vegas, say in a casino, it's very unlikely that some slot machines will have success probability close to 1. We will expect that's more more closely to the lower side, say like 0.3, may be the best success probability if we're actually looking at slot machines in Las Vegas. Yeah, so based on some simulations, we choose different parameters for the two PFA protocols that I've mentioned before. So for elimination tournament protocol, we choose n equals to 1,000, m equals to 20. So recall that m is the threshold to determine whether we eliminate an arm or not. And n is the number of times that we alternate playing two arms for about 1,000 times. And for the aspiration level, we take lowercase m to be 100. So we take there are 100 possible ranks, and m1 here is the m stop. So the threshold that we stopped the protocol. So the threshold that we declare a real arm wins the tournament is 20, and the threshold that we decide to switch is only 3. So if the arm if the counter reach -3, so if the counter if the real arm has a failure for 3 times against the virtual arm, then we basically eliminate that real arm temporarily and move on to the next arm. And if the real arm wins for about 20 times against the virtual arm, then we say that it's the winner of the whole game, and we keep playing that real arm from then on. So that's how we choose the different parameters. And and with those choices, the elimination tournament actually gives us we'll use about 100K states, and the aspiration level protocol used 115K states. So this may seem quite a lot of states. They can actually be encoded using 17 bits. And given that given the number of neurons in human mind, this should not be a problem. So we can safely assume that people can actually remember quite a lot of things if we're considering the number of neurons in human brain. And again, those parameters are chosen so that we can minimize the number of states while still having a relatively good performance. And again, as I mentioned, we want to compare our proposed PFA protocols to some well-known MABs, to some well-known MAB protocols. As you can see in the graph, we basically compare them with epsilon greedy and Thompson sampling. And at about 50K steps, the cumulative regret of epsilon greedy has already exceeded that of the two proposed PFA protocols. So our simulation actually showed that both PFA protocols will eventually outperform epsilon greedy, and not too far from Thompson sampling if we're looking at the difference between the success probability of the chosen arm and that of the optimal arm. So we can claim from simulation that our two proposed PFA protocols are nearly optimal, and they're not too far from the other two MAB protocols, even though the other two require infinite many of states. And again, also we note from simulation that the performance of the PFA protocols decrease greatly significant cognitive bias as we decrease the number of states. For example, if an agent decreases M switch, this increases the negativity bias because you're more likely to give up on an arm that might be possible. Say, if we only take M switch to be 1, then if the real arm, we immediately move on to the next arm. That incurs more negativity bias. Also, the impact of decreasing M in the elimination tournament also have some similar effect. So the bottom line is that these protocols exhibit apparently irrational behavior for some quite rational reasons, because they have limited memory resources. To quickly conclude, in this paper we have, is there some questions or?
Do you hear me?
Yeah.
Okay. Yeah. So yeah, thank you a lot for your presentation.
Oh, sorry. I think there's still two slides.
Two slides. Okay. I'm sorry. I thought you concluded. Okay. Yeah, I have some questions at the end. So go on.
Okay. Yeah. So I'm just no problem. Just to quickly conclude. In this paper, we have proposed two finite state protocols, the elimination tournament and the aspiration level. Both perform quite optimal. Switching costs between arms, the aspiration level protocol is a better choice. And recall that, as I mentioned earlier, our motivation is to understand human behavior. And the fact that the aspiration level protocol exhibits such human behavior, including adjusting aspiration levels according to feedback and optimistic bias, it suggests that humans are not being so irrational. We can further extend our work to the dynamic setting, in which the distributions of arms may vary over time. A simple change to the protocols is to randomly restart the process. Also, as we are currently looking into some more game theoretic interactions, we focus on a concrete example of the wildlife poaching game, in which the ranger is trying to protect some rhinos from the poacher. Both the poacher and the ranger will decide which side to visit strategically, and they will update their strategy based on the behaviors they observe from their components. We're interested in the poacher and the ranger also as resource-bounded agents, so they can also be ruled as facing a dynamic MAB problem. Okay, yeah, and that's all about the presentation, and I would like to open the floor for some questions.
Yeah, thank you, Lily, for the presentation. I'm sorry for the previous interruption. I had some bug, so I thought that you concluded or you stopped presenting, and so I didn't hear that. But thank you very much. Now I would like to encourage the online audience to ask whatever clarifying questions or anything that comes to your mind. I will ask Lily, and I think she will She will be very happy to answer any of your questions. I have some questions here on YouTube, and then I have some my own questions. So Lily, can you please go back a few slides back when you compare various strategies? Yes, here, exactly. Can you please remind us what are the steps here? Is it like playing the arm, or what is the step?
Yeah, exactly. So each step, which is basically mean you're pulling an arm, and that is determined by various protocols. So each protocol will tell you which arm to pull at each step, and every time you pull an arm, that might incur a regret in between of. So the regret here, which is the difference between the best possible success probability and the success probability of the arm you choose to pull.
Yes. Do you hear me? Okay.
Yeah.
I'm sorry. I'm just getting some bugs here, but I think.
Oh, okay. So. Oh, okay. So I can you hear me clearly now?
Yes. Now it's fine.
Okay. Okay. Cool. Yeah. So what I'm saying before was just that that each step is essentially means that you're pulling an arm, and the arm you pull will be determined by different protocols.
Okay. And so basically that's the intuition, or basically I have a question here. What's the intuition for where the new proposal comes from, or where the new proposal performs better than others? What's the intuition behind that?
Yeah, I always think the proposals are there are I think the first is that the proposed protocols are finite state. So basically they use finitely many of states, whereas both epsilon greedy and Thompson sampling are using infinite many of states to keep track of all the past history, which is not quite human-like. And second, I think the proposed protocols are nearly optimal because if we're looking at the gaps here, as I show, those are the difference between the success probability of the chosen arm and that of the optimal arm. So you see the gaps of those two proposed protocols are quite close to Thompson sampling, and it's even better compared to epsilon greedy. So it's nearly point of the two proposed protocol are they're more human-like. As I mentioned before, like how we design the protocols, there are lots of cognitive heuristic involved in designing protocols. So that's what we expect that people might consciously or unconsciously be doing when they're actually gamblers playing the slot machine. So I think those are the strategies of our proposed protocols.
And I also have a question. I think you already concluded in one of your last slides, but again, can you briefly summarize what findings about human behavior you found here, or what the justification for human irrational behavior or deviations from human behavior you find by this work?
Yeah, that's a good question. So yeah, again, the high level goal of
Hello, I think we lost Lily. Is she here?
Oh, I can.
Hello.
I can hear you.
You can hear us. We have small bugs here. I think it disconnected you. So Xian,
can you...
how should we proceed? Okay.
Okay. Can you hear me okay now?
Yes, now I hear you.
Oh, okay. Yeah, so okay, yeah. So what I'm saying is, so I think that the main goal of our study is to try to understand, to explain some seemingly irrational behaviors by saying that people are actually quite rational, but they have limited resources. And the resource we are focusing here are the memory resources. So basically, we don't allow infinitely many memory slots, but we're just using some finite states. So that's why we're trying to use the PFA, the Probabilistic Finite Automata, to model resource-bounded agents. And the finding is that, so if we incorporate some cognitive heuristic while designing the protocols can actually give a quite reasonable performance compared to some other known protocols for the MAB problem. And it's nearly optimal given, as you can see in the graph that I showed before, in terms of cumulative regret and also the limiting average regret. So based on some performance metrics that we mentioned before, the protocols are performed quite well.
Yes, thank you for your answer. And I would like to ask also, considering that there are, or if researchers come with more human biases, how difficult would it be to incorporate it in your work? And specifically, I'm talking about the aspiration level and so on. Would it be would it be difficult to model more biases in such work?
Yeah, I think so. So you basically ask, can a model capture, I guess, more biases?
Yes,
if I understand the question.
And yes, and would this approach still be more or less appropriate for it if it was more biases, if it was able to concern more biases?
Yeah, I think that's a great question. I think so. The current protocol capture, I guess, the three biases I've mentioned before, and I think if we later figure out that, like in reality, people exhibit some other biases, and I think we can modify the protocols to also incorporate those, because I think the work we have done so far is based on more of theoretical work and using simulations to evaluate performance. I think going on, we can for sure involve, I guess, more human experiments to see what people are actually doing when they are making similar decisions, and to see if there are some other some biases that we haven't thought of before, and to, I guess, to change to modify the protocol to incorporate more biases.
Yes, thank you for your answer. If I can elaborate on that, if anyone from the online audience is interested in similar topics, there is a research area called rational inattention. Then economics agent make seemingly irrational decisions, but they do it because making a rational one would cost them a lot of time or another resources. And I think this work is related to this field. Lily, you also mentioned, and I quite like it, the use case with rangers. So can you talk more about it? Because I think that's we are in AISC, we are very interested in products and real world applications. So can you briefly say how it relates?
Yeah, sounds good. So that's actually the current project I'm working on. It's like an extension of the work I just presented, and it looks into the game theoretic interactions between poacher and ranger. I guess I can talk a bit more about the setting. So it's like a wildlife poaching game where you have the poacher and the ranger, and the poachers are trying to catch as many rhinos so they have multiple sites. That can be similar to, you can think of it as the slot machines correspond to the sites, and the poacher is making the decision of which side to go to. And it can be seen as an extension of the slot machine example, because if we think of ranger has a fixed strategy, so the ranger always protects the sites with certain probability. So that's basically similar to each arm has a fixed success probability. And the ranger now, the poacher then is like the gamblers choosing which slot machines to pull. But in the game theoretic case, we allow both the poacher and the ranger to update their strategies strategically, so they can so the ranger also get to modify his strategies based on what the poacher is doing, and therefore we can both model them as they're having MAB problem, but the success probability of each arm is actually changing over time. And we hope that we can again use some some PFAs to model them as a memory bounded agents.
Interesting. So have you, because I think you have chosen this specific field or area of poaching game, have you thought about any other application? What would it be?
I think we actually, I think we also talk about some, I guess, real life and business applications. And I think in a sense that our work is very closely to what nudge is about. There's actually a book written by Professor Richard Thaler. He won the Nobel Prize in economics, I think 2012. And that's a book that talks about how we can nudge people to lead to some behavioral changes. So if we are aware of the standard kinds of mistakes that people make as a result of being resource bounded, or we can model them as resource bounded agents, we can think of ways to help people maybe eliminate the mistakes or even exploit a mistake, depending on what our goals are. And actually, I think in our proposed protocol, like the aspiration level protocol, it actually uses some of the biases. We incorporate those biases in our protocols so that it helps to explain human behavior. So I think some real life applications might just to first understand what the biases are and help them to eliminate the mistakes or to exploit those mistakes.
Yeah, I think this what you just said is crucial, because I see application in a broad area ranging from climate change, how to influence people to reduce waste and energy consumption and so on, to other minor fields. So basically, I see a lot of space for reinforcement learning and this kind of setting in economics. So my last question would be regarding the aspiration level. You said that you start with quite high aspiration level, right? And can you just remind me, it's the aspiration level in range from 0 to 1, or?
Yes. So the aspiration level. So basically, we have m possible ranks, and the ranks correspond to the aspiration level, and so basically the level arrange from 1 to m. So it will go from m, and then we start from high from m, and then we keep lowering that all the way to 1. So for if our m is 100, so we start at 100 and gradually from like 99, 98 and keep lowering
meaning 100 the agent is very optimistic, right?
Yeah.
Yes. Yeah. And then you stop regarding the threshold for winning or losing. There
Yeah,
are
and then
M1 and M2.
Yes, exactly. So we stop the comparison based on the thresholds, and if there's a real arm that's above the threshold, then we basically say, okay, we're done with the tournaments, and the real arm is the best one that we can find, and we keep playing that one from then on. So that's basically said. Once we met the threshold, we're satisfied with what we get, and that's the option that we're going to choose. We're going to use afterwards.
Okay. Yeah. Yes, Lily. Thank you very much for your time and presentation and all the questions answered. I won't torture you anymore, but thank you also to everyone who watched us. Just make sure you subscribe to our YouTube channel ML Papers Explained to get notified about all live sessions and other free content we publish. And we currently have 14 different streams on various machine learning topics. Regarding this presentation, we also have a stream in reinforcement learning, so make sure you check it out. And this session was a part of machine learning in economics stream, where we particularly try to focus on behavioral economics. And I hope you enjoyed it, and you come back. Thank you very much. Goodbye.
Yeah, thank you for having me. Thanks.
Bye.